Picture this. An Arleigh Burke-class destroyer on picket station in the eastern Mediterranean, her Aegis radar painting a full hemisphere of sky, 96 MiG, 41 cells loaded and ready. She is, by almost any measure, the most capable air defense surface combatant in the world. And closing on her from the northwest, at roughly 100 knots, is a propeller-driven drone worth somewhere between $30,000 and $50,000. The drone has no warhead, sophisticated enough to sink a destroyer, no stealth coding, no electronic countermeasures, no terminal phase maneuvering. By engineering standards, it's a simple machine, and the captain launches a standard Missile 6. One shot, one intercept, $4 million. That number does not go away. It sits in the magazine tally, in the fleet logistics chain, and eventually in a congressional budget line. And here is the question without a clean answer. If the Navy built a layered defense specifically so it would never have to spend big money stopping cheap targets, why does the math keep pushing the captain toward the expensive round anyway? The answer is not a failure of design. It is something more unsettling. Stay with us. The Arleigh Burke-class has been the backbone of US Navy surface warfare since USS Arleigh Burke commissioned in 1991. 30-plus years later, the Flight 3 variants rolling out of Bath Iron Works and Huntington Ingalls are still recognizably the same ship, but underneath the hull form, almost everything has been upgraded. The AN/SPW-6 air and missile defense radar, fitted to the newest Flight 3s, is roughly 35 times more sensitive than the AN/SPY-1D it replaces. It can track smaller objects at longer ranges and hand-targeting solutions to weapons faster than any previous destroyer radar suite. The ship displaces around 9,500 tons at full load. She carries a crew of roughly 300. Her standard air defense loadout centers on the MiG-41 vertical launch system. 96 cells, each capable of holding one large missile or 4 smaller ones in a quad-pack configuration. The cells are modular. They can carry SM-2 Block 3 for medium-range area defense, SM-6 for extended range and ballistic missile defense, ESSM Block 2 in quad-pack for close-in engagements, and Tomahawk cruise missiles for land strike. The ship is not a specialist. She is a platform built to fight across the full spectrum of threats, from subsonic drones to hypersonic anti-ship missiles. What strikes me about this ship, after going through the program documentation, is how deliberately she was designed around layered defense. The logic is almost architectural. Long-range missiles handle threats far out. Medium-range missiles catch what gets through. ESSM handles the inner layer. And at the very last line, Phalanx CIWS, the close-in weapon system, that 20mm rotary cannon on its distinctive white dome fires autonomously at anything that has survived everything else. Each layer is supposed to reduce the burden on the one inside it. The whole system is designed so that the expensive SM-6 shot is a last resort for the genuinely dangerous target, not a routine expenditure against a slow propeller drone. And yet, here is the part that seems to make no sense until you run the geometry. An SM-6 has an engagement range of roughly 150 nautical miles against air-breathing threats, possibly more in certain configurations. That number is not publicly confirmed to the decimal point, but the general envelope is well documented. An Arleigh Burke's Phalanx CIWS Block 1B engages targets at roughly 1 to 2 nautical miles. Call it 2 kilometers of effective outer envelope for the gun, with the inner kill zone tighter still. Between those two numbers, 150 miles and 2 miles, sits an enormous gap, and inside that gap lives most of the decision-making problem. Now put a drone in the picture. A slow propeller drone. The kind modelled on commercially available airframes, flying at perhaps 90 to 120 knots at low altitude, is not fast. Against an F/A-18 Super Hornet or an anti-ship cruise missile, the engagement geometry is straightforward. The threat moves quickly, the window is short, and everyone agrees you shoot early. But a slow drone appears to give the defending ship abundant time. It is closing at a walking pace compared to a supersonic missile. The radar sees it early. The fire control solution updates continuously. On paper, there is no rush. On paper. What actually happens is that a low-altitude, slow-moving drone is one of the hardest targets for a ship's fire control system to engage efficiently. It flies in the radar clutter near the sea surface. Its radar cross-section may be small. And critically, its approach geometry means the engagement window for the Phalanx CIWS, the cheap layer, is measured in seconds, not minutes. The gun can slew and track. But confirmation, arming, and the physical time required to put rounds on target at close range against a target that may be approaching from an oblique angle all compress that window dangerously. You'd think a system that fires 4,500 rounds per minute would have all the time in the world. It doesn't. The math on the terminal phase runs the wrong way. Here is what that engagement clock actually looks like. A drone at 100 knots, detected at 15 nautical miles, a reasonable radar detection range for a modern Aegis suite, even against a small target, gives the ship roughly 9 minutes of total engagement time. That sounds like plenty. Except that 9 minutes is not uniformly useful. The first several minutes are assessment time. Is this a hostile drone or a misidentified civilian aircraft? What is its trajectory? Is it a single asset or part of a coordinated wave? The Aegis system processes the track continuously, but the decision to shoot, especially the decision to spend a major missile, involves human confirmation at multiple levels. By the time track assessment is complete, threat classification is confirmed, and a weapons solution is generated and authorized, a significant portion of that 9-minute window has elapsed. What remains may look adequate for the Phalanx CIWS, but here is the complication. If the ship waits for the drone to enter the CIWA's engagement envelope and then the gun malfunctions, or gets pulled to a simultaneous second track, or the drone jinks at the last second, there is no recovery shot. The drone is already inside the minimum range of every other system on the ship. The SM-6 does not have that problem. It can be launched at 100 miles and intercept the drone far outside any threat radius. It solves the geometry problem completely. The captain knows this. The combat systems officer knows this. And when a drone is closing on a picket ship, that is the outer layer of a carrier strike group's defense, a ship that, if disabled, leaves the entire group's early warning capability degraded, the logic of the expensive shot becomes very hard to argue against. One cheap drone costs around $50,000. The Interceptor that stops it costs over $4 million. The math runs the wrong way, and it runs that way by design. Not by the Navy's design, but by the attackers. Let's talk about what that math means at scale, because this is where the economics stop being an accounting problem and start being a strategic one. An Arleigh Burke carries 96 MiG-41 cells. Not all of them are loaded with SM-6. A typical strike group loadout balances SM-6 for area defense, SM-2 for medium-range threats, ESSM for inner layer defense, and Tomahawk for land attack. The SM-6 allocation, the expensive, long-range interceptor, might represent somewhere between a quarter and a third of those cells on a combat deployment, depending on mission profile. Call it 20 to 30 rounds. Now run a scenario. A coordinated drone campaign, the kind that has become a doctrinal tool for several actors in recent years, launches 15 drones against a destroyer on picket station over 3 hours. If each drone forces one SM-6 expenditure, the ship has burned somewhere between half and 2/3 of its high-end interceptor capacity against targets that cost, in total, less than $1 million. And the MiG-41 cells do not reload at sea. There is no deck crew pulling new rounds from a below-deck magazine during the fight. What goes out does not come back until the ship makes port, potentially days or weeks away, depending on the operational situation. What's most surprising about this problem isn't the cost of the individual shot, it's the cumulative magazine pressure. A campaign that cannot sink a single ship can still degrade the entire strike group's defensive depth simply by forcing expenditure. The attacker does not need to get through the defense. They just need to make the defense spend itself. This is the trap, and it was not stumbled into accidentally. Going through open source analysis of drone campaign doctrine from the last several years, one pattern keeps appearing: the deliberate use of cheap, slow, low observable drones, not as primary weapons, but as magazine depletion tools. The drone that forces a $4 million SM-6 launch is not necessarily trying to hit the ship. It may be trying to empty the ship's most expensive defensive capacity before the real threat arrives, whether that is a follow-on missile salvo, a submarine maneuver, or simply a shift in the tactical balance that makes the now depleted destroyer more vulnerable to the next phase. The cheap drone is not the weapon. It is the budget-draining distraction that makes the next weapon more dangerous. Here is a take that will probably generate some pushback. The US Navy's layered defense architecture is brilliantly engineered for the threat environment of 20 years ago, and its magazine economics are becoming a liability precisely because adversary doctrine has evolved to exploit the gap between layers. The Phalanx CIWS is a remarkable system. Autonomous, fast, proven. But it was designed for a different threat density than the one emerging from current drone proliferation. The gap between the SM-6's 150-mile reach and the CIWS's 2-mile reach is not a design flaw. It was intentional, different weapons for different threat categories. What has changed is that a category of threat now exists specifically designed to exploit that gap. Slow enough to be dismissed as low priority, cheap enough to deploy in numbers, and numerous enough to force the captain's hand on the expensive shot before the real attack even begins. The question this raises, and it is one the Navy is actively working through, is whether the layered defense needs an intermediate layer, something faster than a gun, longer range than CIWS, and cheaper than an SM-6. The answer the service has been developing involves several threads. The AN/SEQ-3 laser weapon system, tested aboard USS Ponce and subsequent platforms, demonstrated directed energy engagement of small UAVs. The high-energy laser with integrated optical dazzler and surveillance system, Helios, has been fitted to USS Preble and tested operationally. These systems can, in principle, engage small drones at close range for a cost measured in dollars per shot rather than millions. But they are range-limited, weather-affected, and not yet integrated into the Aegis combat management system as a primary engagement layer. They exist at the margin of the solution, not yet at its center. Put yourself in the combat systems officer's chair for a second. You have a Helios system that might work against this drone if conditions are right. A Phalanx that will definitely work if the drone gets close enough, an ESSM that is cheaper than an SM-6 but still costs several $100,000, and an SM-6 that will absolutely intercept this target right now, at range, with near certainty. And you have, by your calculation, about 4 minutes before the geometry becomes uncomfortable. What do you reach for? The ESSM Block 2, the evolved Sea Sparrow missile, is worth examining here because it sits in the gap between Phalanx and SM-6 in a way that often gets compressed out of public discussion. An ESSM Block 2 costs roughly somewhere in the range of $1 to $2 million per round, depending on production lot and configuration, substantially cheaper than an SM-6. Its engagement range against air-breathing targets is shorter, roughly 27 to 50 nautical miles in various configurations. But that range is still far beyond Phalanx, and the Interceptor's speed and agility make it highly effective against the kind of maneuvering drone that might challenge a gun solution. In quad-pack configuration, 4 ESSM fit into a single MiG-41 cell, which means the ship can carry a much larger inventory of them relative to SM-6. In theory, the ESSM is the right tool for many of the drone intercept scenarios driving the magazine economics conversation. It is cheaper, it is plentiful relative to SM-6, and its engagement geometry covers the band where slow drones present the most complex intercept problems. Inside SM-6's ideal range, but outside CIWS's reliable range. In practice, the decision to use ESSM rather than SM-6 involves its own considerations. Track confidence, threat classification, simultaneous engagement requirements. If the combat picture shows multiple tracks and the captain needs to hold SM-6 capacity for a potential follow-on ballistic missile threat, ESSM may be the preferred solution. But if the track is ambiguous, if there is any possibility the drone is a precursor for something faster behind it, the pressure toward the higher-tier interceptor is real. The system is designed for flexibility. The human operating it is managing risk in real time with incomplete information. That is not a systems failure. That is the nature of combat decisions. The magazine problem has a supply chain dimension that rarely surfaces in the public conversation about drone defense, but it is arguably more significant than the per-shot cost. The United States maintains stockpiles of SM-6 interceptors at naval magazines distributed across the Pacific and Atlantic theaters. The production rate for SM-6, manufactured by Raytheon Technologies, is not publicly specified to the unit, but open-source reporting and defense budget documents suggest annual production capacity is measured in hundreds of rounds per year, not thousands. Against a threat environment that can generate hundreds of drones per engagement, that production arithmetic deserves attention. Here is what the budget documents show. The Department of Defense has requested and received funding for SM-6 procurement across multiple fiscal years, with unit costs that have risen as the missile has become more capable. The FY 2024 and FY 2025 budget requests showed SM-6 procurement in the range of several hundred rounds annually, at a program unit cost that has climbed as block. I gave way to block IB and the extended range variant. The per-round cost number, roughly $4 million, is a program average that includes development and overhead. The marginal cost of a single additional SM-6 in production is lower, but the production pipeline has finite throughput. What this means operationally is that a sustained campaign forcing SM-6 expenditure at even modest rates begins to stress not just a ship's magazine, but the entire theatre resupply chain. Restocking a destroyer after a high-tempo engagement requires pulling rounds from a limited inventory, transporting them to a port, and conducting an alongside replenishment. A process that takes the ship off the line for hours at minimum, potentially days. From a fleet management perspective, what this tells us about the current era of naval warfare is that the most dangerous characteristic of drone proliferation may not be the lethality of individual drones. It may be the logistics pressure that sustained drone campaigns impose on an adversary's most expensive defensive assets. The side that can generate cheap, expendable threats faster than the other side can replenish expensive interceptors has found a form of economic leverage that does not require winning a single engagement outright. Beijing's naval planners have studied this arithmetic carefully. The Type 055 destroyer, China's most capable surface combatant, comparable in some respects to an Arleigh Burke but larger, carries its own vertical launch magazine and faces its own version of these trade-offs. But China's drone and anti-ship missile development programs have been specifically oriented toward generating the kind of salvo density that stresses US Navy magazine capacity. The DF-21D and DF-26 anti-ship ballistic missiles are the headline threat, but the lower tier, cheap drones and subsonic cruise missiles in numbers, is the layer that does the economic work before the ballistic missiles are ever launched. This is not speculation. It is the stated logic of anti-access/area denial doctrine as it has developed over the last 2 decades, and it appears in the open literature from Chinese military academic journals as clearly as it appears in US defense analysis. The Arleigh Burke on picket station is not just defending herself. She is a node in a network, the forward sensor and shooter that gives the carrier strike group its extended defensive reach. If that node is degraded, not sunk, just depleted of high-tier interceptors, the entire network's capability drops in ways that are hard to recover from quickly. The attacker doesn't need to win the engagement. They need to change the captain's calculation. A $100 drone can do that if it arrives at the right moment in sufficient numbers. Here is where the geometry closes. The Arleigh Burke-class is not standing still on this problem. The Flight 3 configuration with AN/SPW-6 radar represents a substantial improvement in the detection problem. Smaller targets at longer ranges, earlier track establishment, more time for the full engagement sequence. That earlier detection window is real and meaningful. If a drone is tracked at 30 nautical miles rather than 15, the 9-minute engagement clock becomes 18 minutes, and the case for waiting, for letting the CIWS or a directed energy weapon take the shot at close range, becomes more defensible tactically. The question is whether the detection improvement is enough to shift the fundamental economic logic. What the numbers suggest is that it helps, but it does not resolve the underlying asymmetry. An earlier track gives the captain more time, but it also gives the adversary's planners more information about detection thresholds, and they will adjust. Drone campaigns have already demonstrated adaptation in altitude, route planning, and electronic signature management. The competition between detection and evasion is continuous. What would actually change the economics is a cheap, reliable, long-range kill option in the engagement band between CIWS and ESSM. Something with a per-shot cost measured in thousands rather than millions, sufficient range to intercept before the terminal geometry becomes critical, and enough throughput to engage multiple simultaneous tracks without depleting any finite magazine. Directed energy is the theoretical answer. High-power microwave systems, currently in testing, can engage drone swarms with effectively unlimited magazine depth. The only consumable is electricity, generated by the ship's own power plant. The problem is range, adverse weather performance, and integration with Aegis fire control. USS Portland demonstrated a laser weapon successfully disabling a drone target in 2021. The results were encouraging. The operational integration, getting that capability into the same fire control loop that manages SM-6, ESSM, and Phalanx, so that the combat systems officer can assign threats to layers as smoothly as the current system does, remains a work in progress. Until that integration is complete, the captain's hand will continue to be pushed toward the expensive round when time pressure, geometry, and the cost of being wrong all converge in the same engagement. This, ultimately, is the answer to the paradox posed at the start. The Arleigh Burke does not burn a $4 million SM-6 on a $50,000 drone because the system is badly designed. She burns it because the attacker specifically engineered the situation so that every cheaper option carries a meaningful residual risk, and the cost of that residual risk. A degraded picket, a hole in the carrier strike group's early warning, potentially a multi-billion-dollar ship damaged in the terminal phase, exceeds the cost of the Interceptor. The SM-6 launch is not a mistake. It is a rational response to a trap that was built to be rational to walk into. That is what makes it effective as a strategy. The attacker doesn't need to beat the SM-6. They just need to make it worth firing. The human cost of this dynamic is less visible than the dollar figures, but it is real. Arleigh Burke destroyers have been among the most operationally stressed platforms in the US Navy surface fleet for the better part of a decade. Deployment lengths that were once nominally 7 months have stretched, in some cases, to 9 or 10. Maintenance availabilities have been compressed. The pace of operations in the Red Sea, the Eastern Mediterranean, and the Western Pacific has generated a tempo that puts sustained pressure on crews of roughly 300 people operating complex systems at high readiness for extended periods. A destroyer on picket station is not a ship at rest. The radar is always on. The combat systems watch is always manned. The MiG-41 cells are always loaded. A crew that has been at sea for 7 months running air defense engagements, tracking drones, evaluating threats, making expenditure decisions under time pressure, is a crew operating at a level of sustained cognitive load that has measurable effects on decision quality over time. The Navy has acknowledged this through force structure requests and readiness reports. The number of Arleigh Burke-class destroyers currently in the active fleet, roughly 70 at various stages of commission and availability, is considered insufficient to meet the simultaneous operational demands of combatant commands across multiple theatres. Bath Iron Works and Huntington Ingalls, the two builders, are working to maintain a construction pace sufficient to replace ageing hulls and grow the fleet modestly, but shipyard capacity constraints and workforce challenges have made schedule slippage a consistent feature of recent build programs. Compare that construction pace to what is happening in Chinese shipyards. The People's Liberation Army Navy has been commissioning new combatants, including Type 055 destroyers and Type 052D guided missile destroyers, at a rate that has no recent parallel in naval history outside of wartime production. Estimates from the Office of Naval Intelligence and the Pentagon's annual China Military Power Report suggest the planned surface fleet has grown dramatically in the last decade, both in numbers and in capability. The fleet balance that existed 15 years ago has shifted, and the trend line is not moving in a direction that makes the magazine economics problem easier to manage. This is the strategic dimension behind the $4 million intercept. It is not just about one shot in one engagement. It is about whether a naval force optimized for capability per unit, producing extremely capable, extremely expensive ships at a relatively modest rate, can sustain the attrition economics of a threat environment deliberately designed to exploit the cost asymmetry. The Arleigh Burke is a remarkable machine. The question is whether the industrial base and force structure behind it can generate enough of them, supplied with enough interceptors, to hold the economics equation in balance over time. There is a line in the FY 2025 shipbuilding budget request that stuck with me. Not a headline number, but a footnote about extended delivery timelines for DDG-51, Flight 3 destroyers due to material availability constraints. Shipbuilding is a long-cycle business. The consequences of production gaps today show up in fleet capacity a decade from now. The drone that forces a $4 million SM-6 expenditure today is also, in a diffuse way, part of the pressure that makes those future capability gaps consequential. Here is what all of this adds up to in operational terms. The Navy's response to the magazine economics problem has several moving parts, all in motion simultaneously. The Conventional Prompt Strike program is developing intermediate-range hypersonic weapons for offensive strike, less relevant to the defensive problem, but part of the overall deterrence calculus. The development of SM-6 Dual extended range capability increases per-shot effectiveness, improving the cost efficiency of each expenditure. The integration of directed energy weapons is moving forward on multiple platforms, and the integrated air and missile defense capability of the Aegis system continues to improve through software updates that allow more intelligent threat prioritization and engagement sequencing. The most direct short-term answer to the magazine problem, though, may be doctrinal rather than technological. There is a developing body of thought in surface warfare communities around threat prioritization and engagement ladder management. The deliberate sequencing of which layer engages, which category of threat, with clear pre-authorized decision trees that reduce the cognitive burden on the combat systems officer in high-tempo engagements. If the captain can pre-designate that slow, subsonic, single-track drones below a certain size threshold are CIWS or directed energy targets unless they enter a specific engagement zone, the SM-6 inventory is protected for the threats that actually require it. Will it fully solve the problem? Comment YES if you think directed energy and better doctrine can close the cost gap. Or no if you think the magazine economics are a structural problem that technology alone won't fix. We read every comment. The challenge with pre-authorized engagement rules is that they assume the threat is what it appears to be. A drone that looks like a cheap nuisance and behaves like a cheap nuisance until it is 2 miles from the ship, at which point it deploys a submunition or triggers a sensor, is a drone that exploited the engagement ladder. Adversary planners understand engagement doctrines. They design threats to the edges of those doctrines. The captain who follows a pre-authorized decision tree too rigidly in a dynamic threat environment is vulnerable to being outthought. The captain who deviates from it and reaches for SM-6 every time generates exactly the magazine pressure the attacker is trying to create. There is no clean solution. That is the honest answer. The Arleigh Burke on picket station in the Eastern Mediterranean is not making a mistake when she fires the SM-6. She is making the most defensible decision available under the conditions she faces. The systems surrounding her, the combat management software, the fire control radar, the tiered weapon inventory, the doctrine she operates under, is the product of decades of engineering and operational experience that is, by any reasonable measure, the most sophisticated surface air defense capability ever deployed. The SM-6 itself is a weapon of remarkable range and precision, capable of engaging targets that no previous ship-launched interceptor could reach. And yet a $50,000 drone can put the captain in a position where that remarkable weapon is the only reliable choice, and can do so not once but repeatedly across a sustained campaign against a ship that cannot reload until it leaves the theater. The asymmetry is not an accident. It is a feature of the threat, not a bug in the defense. What changes the equation in the long run is not finding a way to make the SM-6 cheaper, though production scaling helps, or finding a way to make the drone more expensive to build, though export controls and supply chain pressure matter. What changes the equation is fielding a kill option in the engagement band where the economics are worst. Longer than CIWS, shorter than SM-6, and cheap enough that each shot does not register as a strategic expenditure. Directed energy is the candidate. The timeline for operational integration is measured in years, not months. Until then, every destroyer on picket station carries the same arithmetic, 96 cells, a magazine that cannot be refilled at sea. A threat environment that has learned to count those cells and do its own math. The loop that opened this closes here, and it closes on a genuine dilemma rather than a verdict. The US Navy built the most capable layered air defense surface combatant in the world, and adversary planners studied that system until they found the seam. The geometric and economic gap between what the cheap layer can reliably do and what the expensive layer costs to use. The Arleigh Burke is not outmatched. She is being used as a mathematical tool by an attacker who understands that making her spend is almost as useful as making her burn. The question the Navy, and the Defense Industrial Base, and the congressional committees that fund both, has to answer is not really about any single ship or any single engagement. It is about whether the fleet that exists can generate enough capacity, sustained over time, against a threat environment specifically engineered to erode that capacity one expensive intercept at a time. Does the fleet hold fire and trust the close-in gun? Or does it spend the expensive round and protect the picket? Every choice has a price. The attacker built the situation so that both answers are costly. That is not a problem you solve in a single engagement. That is the strategic competition itself, measured out $4 million at a time. If you want to understand how the carrier strike group that depends on that destroyer for its early warning is structured, and what happens to the whole group when the picket is degraded, that breakdown is coming next. If this one gave you something to think about, the algorithm responds to comments more than likes. Leave your take below.